this is Teen Nights, and we're teaching our final project. My name is Elizabeth Phillips.
And I'm Allison Harper.
So we're going to go ahead and dive right in. For question 1, Allison, solve each diagram below.
Okay, so for these diagrams below, the concept is the two numbers in the circle added together are supposed to equal the number in the middle. So to figure out our first circle, we are going to take 15 and subtract 7 from it, and we get 8. Same for the next. 20 minus 8 is 12. 17 minus 12 is 5. And then we're going to go back and check to make sure that we did this correctly. So we're going to do 7 plus 8 is 15. 8 plus 12 is 20. 12 plus 5 is 17. And 5 plus 7 is 12. So now we have checked our work and we know that we did everything the right way. So next example, we're going to do the same thing. 13 minus 6 is 7. 21 minus 6 is 15. 19 minus 15 is 4. And then we're going to go back and check. So 7 plus 6 is 13. 6 plus 15 is 21. 15 plus 4 is 19. And 7 plus 4 is 11. So all of those are correct. Next example, 6 minus 3 is 3. 12 minus 3 is 9. 15 minus 9 is 6. So let's go back and check. 9 plus 6 is 15. 6 plus 8 is 9. But if you notice in our diagram, we have an 8 here instead of a 9. So that is not correct because 6 plus 3 equals 9, not 8. So this diagram has no solution. And our last one, 9 minus 8 is 1. 7 minus 1 is 6. 16 minus 6 is 10. Uh-oh, might have to move this for a sec so we can see our numbers. 8 plus 1 is 9. So that one is correct. 1 plus 6 is 7. So that is correct. 6 plus 10 is 16. That one is correct. And 10 plus 8 is 18. So this one checked out as well.
Good job, Allison. That was easy to follow along with.
Thank you. Okay, so Elizabeth, what is the perimeter? What is perimeter and what are the perimeters of these shapes?
So what we're going to do, if we'll look at our shapes, all of them have different sides. One side is going to be equivalent to 1 unit. So when we look at our square and we go ahead and count up all the sides, we're going to have 1, 2, 3, 4 sides, which means that our perimeter will be 4 units. Perimeter is basically adding up all of the sides of a shape together to get one whole number. So again, for our triangle, we're going to count up the sides. We have 1, 2, 3. So our triangle's perimeter is going to be 3 units. And for our next shape, we have 1, 2, 3, 4, 5 sides, which means that our perimeter will be 5 units.
Great, thank you, Elizabeth. That was very easy to follow and understand.
Thank you. So Allison, which figure has the least perimeter and which has the greatest perimeter?
Okay, so Elizabeth just explained perimeter to us, so that makes this problem a little bit easier. So we're going to go ahead and count up all of our sides for our shapes. So the perimeter of this first shape is 16. The perimeter of this one is 12. For this one is 14, 20, 14 again, 18, and 16. So if we look at all of our shapes and their perimeters, the least or the smallest number is 12. So this will be our shape with the least perimeter. And then 20 is the greatest or largest perimeter. So that was pretty simple.
You did a good job explaining that.
Thank you. Okay, Elizabeth, find the least common multiple for the numbers 48, 25, and 65.
So what we're going to do first, we want to break all of our numbers down to until we can't break them down anymore. So what we're going to do first is we're going to go ahead and divide all of our numbers by 3. And when we do that, we're going to get 16, 25, and 65. So next we're going to divide all of our numbers by 5. And when we divide all of our numbers by 5, we are going to get 16, 5, and 13. If you'll look at your last two numbers, your 5 and 13, you'll notice that you can't break these down anymore. So they're all finished up. But our 16, we can still break down some. So we're going to go ahead and divide that by 2. And we're going to have 8, 5, and 13. We're going to divide it by 2 one more time. We're going to get 4, 5, and 13. Our 4 can still technically be broken down, so we're going to divide by 2 one more time, and we're going to have 2, 5, and 13. Those will be our least common multiples.
Thank you. You explained that very well.
Thank you. So Allison, show the Indo-Arabic equivalent to each of the following.
Okay, so if you look at the figure over here, it's just a bunch of shapes. So how in the world are we supposed to turn that into a number? Okay, so we have a little key over here that shows us that the triangular looking shape is equal to 1, and the one that looks like a little arrow pointing to the left is equal to 10. So what we're going to do, since we have 4 of the little arrows, we're going to say 4 times 10, which gives us 40. And the triangle is equal to 1, and we only have 1. So 1 times 1 equals 1. And then we're just going to simply add 40 and 1 together, which gives us 41. So this figure up here, or these shapes, are equal to 41.
See, that's pretty neat, Allison. I really liked that.
Thank you. Okay, question 6. Write an equation to solve for the following pyramid.
When we go to look at our pyramid, we'll notice that we have an X in there. We're going to want to solve for all the blanks, but we're really looking for our X. So the best way we can start out this pyramid is by looking for the number above 7 and 3. So we're going to set up an equation with 7 plus 3. And when we add those numbers together, we're going to get the number 10, which is going to go in that blank spot. Well, now we need to find the number under 25 right next to 10. The best way to do this would be to do 25 minus 10, which will give us 15. So 15 will go in that blank. And afterwards, we can simply subtract 7 from 15, and we should get 8, which will be our X. So we can go ahead and put that in our spot, and our answer for X for our pyramid will be 8.
That was pretty cool.
Allison, demonstrate rounding to the leftmost digit to estimate the rules of each of the following expressions, then make the exact computation.
Okay, so I know that was a long drawn out question. So all we're really doing is we are going to round all of these numbers over here to the left, and then we're going to simply solve. Okay, so our rules for rounding are, if the number is larger, 5 or larger, you round up, and if the number is smaller than 5, you round down. So here's all of our numbers in our equation over here. And what we're going to do, since there's 3 digits, we're going to look at the number in the middle to determine whether we round up or down. So with the number 883, the middle digit is 8. So it's larger than 5. We round up to 900. For 465, our middle digit is a 6, which is larger than 5. So once again, we're going to round up to 500. With 134, the middle digit is a 3, and it is smaller than 5. So we round down. So that number is going to round to 100. So now all we're going to do is solve. So we're going to plug in our rounded numbers that we just discovered. So first we are going to take 900 plus 500, which is 1400. And then 1400 divided by 100 is 14.
That's pretty neat, Allison. I like that.
Thank you. Okay, Elizabeth, 4 married couples belong to a bridge club. Determine who is married to whom, given the following names and clues.
We'll notice right off the bat, Kitty is married to Will. Well, if Kitty's married to Will, that means nobody else is married to him. Next, if we will look at our first clue, Floyd is Josie's brother, and our last one, Anne's husband is an only child. Floyd technically cannot be married to Anne because he has a sibling, and he can't be married to Josie because Josie is his sister, which means that Floyd will have to be married to Sarah. Next, when we look at our second clue, Josie and Gus dated some before Gus met his wife. Well, if Josie has already dated Gus but isn't technically married to him, that means that he will not be a part of, or he will not be married to Josie, basically. Josie can't be married to Floyd either because Sarah's married to him, and she can't be married to Will because Kitty's married to him, which means Josie would have to be married to David. And since we already figured out who's married to who for the first 3 people, our last lady, Anne, is going to have to be married to Gus because nobody else is, which means that Kitty will be married to Will, Sarah will be married to Floyd, Josie will be married to David, and Anne will be married to Gus.
Great job explaining that. That can get a little confusing, but you did a really good job of clearing that up for us. Thank you.
Thank you. So Allison, create a chart for each of the following to demonstrate how you perform arithmetic in bases other than 10.
Okay, so here we are going to be doing a base 5 problem. And the only numbers that can be in our answer are 0, 1, 2, 3, and 4. And okay, so first things first, we're gonna take 2 plus 3, which equals 5. But if you notice, 5 is not one of our numbers that can be in our answer. So what we do is we do 5 minus 5, which is 0. So we put our 0 and we carry our 1. So then we add up all of these numbers, 1 plus 3 plus 3. Sorry, trying to move this where we can see everything. And 1 plus 3 plus 3 is 7, and that's another number that cannot be in our answer. So then we do 7 minus 5, so we put down our 2, and then we carry our 1. So then we add up all of these, 1 plus 4 plus 1, which equals 6. That is a number that cannot be a part of our answer. So then 6 minus 5 is 1. We put down our 1, and we carry another 1. And since there's nothing under our 1 over here, we just bring that 1 down, and our answer is 1,120 base 5.
You did a good job explaining that, Allison.
Thank you. Okay, what is an example of inductive reasoning?
Right. Inductive reasoning is basically reasoning how a problem will be laid out, kind of having an idea or getting an idea of a pattern that's occurring in a problem or a set of problems. So if we look at our first problem, 6 times 9 plus 4 is equivalent to 58. Now if we look at our next problem, 65 times 9 plus 3 is 588. Now if you look at your numbers, you'll notice that a 5 was added after 6, and our 4 got bumped down to a 3. We look at our next problem. We have 654 times 9 plus 2 is equivalent to 5,888. Well, now we're doing 654, or 654. We're pretty much counting down, times 9 plus 2, or 2 got bumped down again, and it just added another 8 to our answer. So for our next problem, we have 6,543 times 9 plus 1 is going to be 58,888. Now at this point, we'll start to notice that we have a pattern going on. We're counting down from our 6. We're doing 6, 5, 4, 3, and then we're bumping our 4 down 1 digit at a time with every problem that we're doing. So we went from 4 to 3 to 2 to 1, and all it's really doing is adding another 8 to our answer. So if we look at our next problem, notice how we have blanks. Given that we're counting down from our 6, we can automatically assume that our blank spot, or blank number, our number for 6543 after that would be a 2. So we'd have 65,432 times 9, and assuming that our digits, our 4 is still going down a digit with every problem, we can automatically assume that that blank right there is going to be a 0. So our answer for this problem, and you can test it out on a calculator, it's going to be 65,432 times 9 plus 0 is going to be 588,888. So inductive reasoning is pretty much just establishing a pattern and kind of reasoning what the next step in that pattern is going to be.
You did a really awesome job explaining that. That was pretty cool how that works.
Allison, demonstrate how to use the process of 9s to check each of the following answers.
Okay, so I thought this was really cool. I was never taught this in school, but this is a really cool tool to have. Okay, so what we're going to do is we are going to go through and look and see if we can find any numbers, if added together, that equal 9. So in our 416, there are no 9s, but if we look at our 7,490, we see a 9. So we're going to go ahead and cross that out. And in our 69,844, there's another 9. So we're going to get rid of that. And in our answer, 112,790, we're going to go ahead and cross that 9 out as well. But also 7 plus 2 equals 9. So we're going to get rid of those 2 as well. And then we're just going to simply go back and add up our numbers. So we have 4 plus 1 plus 6, which equals 11. But then we're going to break down our 11. And we're just going to do 1 plus 1, and that equals 2. Same for our next row. 7 plus 4 plus 0 equals 11. We're going to break down our 11 to 1 plus 1, which equals 2. And here we have 6 plus 8 plus 4 plus 4, which is 22. And we're going to break that down to 2 plus 2, which gives us 4. Okay, so now we're going to add up all of our answers that we got over here. So 2 plus 2 plus 4 gives us 8. And then we're going to go down here to our answer and add these up. So 1 plus 1 plus 0 is 2. So then we have our 2. But there is an error because our 2 and our 8 are not the same number. So there's an error. And so now we're just going to go back and add this and see what our true answer is. And 416 plus 7,490 plus 69,844 really equals 77,750. So it's just an easy way to check your work to see if your answer is correct.
Allison, that was pretty cool. I like that.
I did too. I thought that was a pretty neat little concept.
Oh yeah. Oh yeah. I wish I knew that in school.
Me too. Okay, so Elizabeth, solve for 273 times 628 using a lattice algorithm. Sorry.
It's all good. If you'll notice below, we have our chart for our lattice algorithm. All we're going to want to do, and if you remember your multiplication tables and whatnot, you'll know, or I guess I shouldn't say multiplication tables. I know a lot of kids growing up would have that big square block that had all the little numbers you could push in with your multiplication, and you'd have to fill out a sheet and whatnot like that. And so this is kind of the same thing, except that you're finding your answers. All you do is you find your 2 for 273 and your 6 for 628. You're going to go across until you find the box that meets between those two numbers. So in this case, it would be the upper left-hand box. So what we're going to do is we're going to start out with our 3 and our 6 in 273 and 628, and we're just going to multiply 3 and 6, and we're going to get 18. So we'll put a 1 in the top left corner and 8 in the bottom right hand corner. Next, we're going to move on to our 7 in 273, and we're going to keep our 6. 7 times 6 is going to be 42, so we'll put a 4 in the top, a 2 in the bottom. For our next number, we're going to do our 2, and we're going to keep our 6. So 2 times 6 is 12. Next, we're going to move down a row, starting from the right-hand side. 3 times 2 is going to be 6. We're going to move left a box, and we'll do 7 times 2, which will be 14. Left a box, and we'll do 2 times 2, which is going to be 4. Then we're going to move down to our bottom row, all the way to the right, and we're going to do 3 times 8, which will be 24, and then 7 times 8, which will be 56, and 2 times 8, which will be 16. Now that we have our whole chart pretty much added up, you'll notice there are a couple of lines going diagonally across your screen. That's actually to kind of help us with figuring out what numbers we're going to add. So in our first little area right below the bottom diagonal, we have a 4. The bottom right hand corner of your chart has a 4. Well, since that's just a 4, technically we don't really need to add anything else to it, so we're just going to put 4 in the bottom of our algorithm, our lattice algorithm. Next, if we look at our diagonal right above that, we have 6, 2, and 6. We're going to add that together, and we are going to get 14. 14 is too big for that spot. We want to have 1 digit, so we're going to move our 1 up to our next diagonal. And it's kind of the same thing with addition. Whenever you go to add a big number and you get 2 digits, you move that 1 up to the next row. So for our next problem, or our next diagonal, we have 6, 5, 4, 0, 8, and now our 1. We're going to add all of those together, and we should get 24. So we're going to keep our 4. We're going to move our 2 up to the next diagonal. Then we're going to add 1 plus 4 plus 1 plus 2 plus 1 plus our 2 that we just moved up there. And that should give us 11. So we're going to keep our 1 that we have in our 1's place. We're going to move our other 1 up to the next diagonal. And we're going to go ahead and add 0, 2, 4, and our 1, which should give us 7. We don't have to carry a number up this time, so we can just move straight to our next diagonal. And we only have a 1. So we just keep our 1. And we should get the answer for 273 times 628. It should be 171,444. And you can double check this with a calculator if you want. This is just a neat little trick to, or a neat little approach to your multiplication tables.
I enjoyed that. That was really cool.
Thank you. Allison, complete parts A through D.
Okay, so we have this cool little figure right here. And I also have a key down here for us. So C is going to be our circular shapes, T will be triangular shapes, L will be large shapes, G will be green shapes, H will be hexagonal shapes, S are small shapes, and R are red shapes. Okay, so A says, which shapes are found in the set L intersection H? So pretty much what we're looking for here are large shapes that are hexagons. So large hexagons are our big hexagon here. Uh-oh. Oh no.
It's going to be that middle.
Okay, sorry. It
It's
took
all
me
right.
to another screen. Okay. Let's try this again. So we're looking for our large hexagonal shapes here. So the big red hexagon and the big green hexagon. Okay, so for B, it says demonstrate which shapes are found in the set C union H. So here we are looking for circular shapes and hexagonal shapes. So the big green circle, the big red circle, the small red circle, small green circle, small red hexagon, small green hexagon, big red hexagon, and big green hexagon. Okay, part C, demonstrate which shapes are found in the set, T and R, but actually there's supposed to be a little line over RT, which means we're going to exclude that. So we are looking for red shapes that are not triangles here. So our big red circle, our small red circle, our small red hexagon, and our big red hexagon. And part D says demonstrate which shapes are found in the set C intersection S intersection R. And I know that sounds so confusing, but we are looking for circles that are small and red, and that's all that means. So small red circles, we only have one. And it did spin, I promise. You just can't tell because it's a small shape. And that's all.
I really liked that, Allison. I'll say one thing. I like the spinning shapes.
Thanks. Okay, create a Venn diagram giving the following information.
To the left of your screens, we're given a blank diagram. The circles are labeled A, B, and C. So our problem is telling us to let the diagram include A, B, C, D, E, F, G, H, where A has B, C, D, G, H, B has D, F, H, and C has D, G, H. So if we'll go ahead, and look at our problems, we'll notice that all of our shapes have D and all of our shapes have H. Again, if we'll just kind of look through all of our letters, we'll notice that none of them have A and E. So now we're going to kind of narrow down our circles. With A and B, they both have D and H. With B and C, they both have D and H as well, which is going to be means pretty much because everything has D and H. D and H are going to go in that little blank right in between all three circles. For our next part of our problem, we're going to look at C and A, which have D, G, and H. So once we kind of, you're good. Once we kind of establish what all goes where, we'll notice that there are a couple of shapes left out. The shapes that are left out are more than likely shapes that go in just one circle, not in multiples. So for example, with A, we don't have B and C included in our little sets that we just made. So B and C are only going to be in the circle for A. Again, with circle B, we don't have F in our little, trying to think of the word, we don't have F in our little things that we made with our letters to determine what goes where. So F is going to be only in B. And when we finally kind of get all this sorted out, we'll eventually have a Venn diagram that looks like the one to the left.
Thank you. That can be a little confusing, but you made it pretty simple and straightforward for us. I appreciate that.
Allison, demonstrate parts A through F.
Okay, so A says which rods will measure the 9 rod. So to figure this out, the first thing that we do is we find the factors of 9. And so the factors of 9 are 1, 3, and 9. And that's how we got our factors. So 1 times 9 is 9, and 3 times 3 is 9. So the rods that will measure the 9 rod will be the 1 rod 9 times, the 3 rod 3 times, and the 9 rod 1 time.
That was pretty easy, Allison.
Thank
I really
you.
like that. Made it easy.
Okay, create a magic square using the following numbers: -7, -6, -5, -4, -3, -2, -1, 0, and 1.
What we're going to want to do first, because we don't know what amount we're needing in each column, row, and diagonal, we're actually going to add all of our numbers that were given together, and we should get -27. So what we're going to do now, because we have 3 boxes in each row, column, and diagonal, we're going to divide -27 by 3, and we should get -9. Well, this just means that we need -9 in each row, column, and diagonal. It kind of makes things a little bit easier as far as solving goes. So next, what we're going to do is we're just going to do a little bit of trial and error, pretty much, because magic squares, honestly, they're mainly trial and error, and eventually we'll find the numbers 0 and 1. So once we get these numbers, we can do a quick little run through just to double check to make sure they're right. So 0 plus -5 plus -4 is -9. -7 plus -3 plus 1 is -9. -2 plus -1 plus -6 is -9. And you can do the same thing for your -4 plus 1 plus -6, and then for that next row and that next row, or column. And you can do the same thing with diagonals. I actually didn't put a 9 there. I didn't think about it, but you can do 0 plus -3 plus -6, and that'll give you -9. And you can do the same thing with -4, -3, and -2, and that'll give you -9, which means that this magic square right here is correct.
Awesome. Thank you for those visuals. They were very helpful.
Thank you. Now, Allison, demonstrate the percentage and fraction of each red portion of these figures.
Okay, so the first thing we're going to do here is, if you notice that this shape was split into 4 equal parts, but then one of our equal parts was split again into 2. So we're going to go ahead and split the rest of our parts. And we see that there are 8 different pieces to this figure. And there is only one section that is colored red. So that gives us a fraction. And that fraction is 1/8. And then now, to turn this fraction into a percentage, we just simply take 1 divided by 8, which gives us 0.125, We are going to multiply that by 100 to get our fraction, which is 12.5%. So this red section is 12.5% of the entire figure. So Elizabeth, can you solve the following word problem? It says, Ashley wants to buy a new bike for $60. Every day when she does her chores, she earns $5. How many days will she need to do chores before she has enough money for the new bike?
Well, if Ashley wants to buy her new bike and she does her chores every day and gets $5 every day, what we can do is we can assume that one day she'll get $5, 2 days she'll get 10. So using this kind of information, we can go ahead and set up a chart. So if you look at my chart to the left, you'll notice that if she works 2 days, then she's going to make $10. And this is a good way to set it up would be to do her $5, her initial $5 times however many days she works, just kind of get an idea of how much money she's going to make. So the next part in our problem, the next row in our problem, is going over or showing that if she works 4 days, then she'll get $20. Again, if she works 6 days, she'll get $30, and if she works 8 days, she'll get $40. So now what we're going to do is we're going to set up a little chart to the right of our screen, which I went ahead and whoop.
Sorry.
You're fine. I went ahead and set up a chart over here. If you'll notice our arrow, it's kind of just showing how much money she makes per day. So we can do this 2 different ways to figure out how many days it's going to take to get $40 for her bike. Or I mean, $60. Sorry about that. Which our chart doesn't show it all the way, but we'll go ahead and get to that in a minute. Let's say, since she needs $60, we can look at our chart. Our money is going up in intervals of 10 for every 2 days that she works. So if she works 8 days and has $40, we can assume that if she works 10 days, she'll have $50. And if she has $50 for 10 days, we can assume that the next part of our problem, or our next step in our sequence, would be that if she were to work 12 days, she would have $60. So we can go that way. We can fill out the rest of our chart and eventually get up to 12 days being $60. Or we can go ahead and look at our chart to the right, which doesn't quite go far enough, but if we really want to, we can get a bigger setup. We can go right 12 on our x-axis, and then we can go up to 60, and that should be where our line intersects with that point that we just found, which means if she were to work 12 days, she would have $60.
You did a really awesome job explaining that. Thank you. That was very clear.
Thank you. So this is the end of our Team Teach. I hope you guys enjoyed watching. I know we had fun teaching it. And Merry Christmas.
Merry Christmas. Thanks for watching, guys.
Bye.